Hello and thank you for joining us for the May session of our GeoStudio Tech Talk. These monthly webinars are designed to improve understanding of the software and ultimately promote success in your engineering projects. My name is Chris Kellen and I'm the Director of Geotechnical Analysis for the GeoStudio Business Unit here at Sequent Bentley. This month's Tech Talk focuses on the analysis of mechanically stabilized earth walls, or MSEs, using GeoStudio. In this Tech Talk, we will briefly review the theory behind modeling soil structure interaction in a limit equilibrium analysis, review the workflow for setting up a basic analysis using geosynthetics, and then delve into the topic of convergence. Once this is done, we will discuss the difference between global stability and internal stability, then review a case study for a 37-meter high MSE wall. Feel free to ask questions at any time in the chat feature, and we will respond as soon as possible in a follow-up email. A recording of the webinar will be made available so that participants can review at a later time. Let's get started with a discussion on the theory. Any geotechnical system with reinforcement constitutes a soil structure interaction problem. Consider the anchor-supported excavation shown here. The load that is transferred into the structure depends on movement in the soil or rock or a post-installation tensioning of the system. The anchor has a free length and a bonded length. Tensioning of the anchor post-installation causes shearing at the interface between the bonded length and the soil or rock. Similarly, deformation behind the wall, as shown here, will transfer load onto the wall. Any bending or shearing in the wall will cause the bonded length to pick up load as it's transferred via the bearing plate through the free length. All reinforcement is fundamentally the same. It is assumed that the soil structure interaction transfers load through the reinforcement and into the ground profile. We must therefore convert the shear mobilized at the interface into a pullout force acting on the sliding mass. The pullout force or reinforcement load depends on a number of factors, including the pullout resistance, which characterizes the shear resistance mobilized at the interface between the reinforcement and the surrounding soil or rock, the area of reinforcement behind the slip surface, the tensile capacity of the reinforcement, a reduction factor to account for lifespan, temperature, pH, and more, and finally the presence of anchorage at the face of the excavation. Let's conduct a simple hand calculation to demonstrate the process of converting shear mobilized into a pullout load for the lowermost geosynthetic in the profile. For this particular trial slip surface, the length of geosynthetic behind the sliding mass is 7 meters. The parameters for the geosynthetic are presented in the table. The pullout resistance and reduction factor are 75 kPa and 1.5 respectively. The tensile capacity is 180 kilonewtons with a reduction factor of 1.5. We can now calculate the factored pullout resistance, FPR, which is the pullout resistance divided by the reduction factor, RF. Given that the reinforcement extends 7 meters behind the trial slip surface, the maximum pullout load is therefore 250 kilonewtons, calculated as 75 divided by 1.5 to give us the factored value of 50 kilonewtons per square meter, and taking that, multiplying by 7 meters of length times 1 meter in the out of plane direction gives us our max pullout load of 250. Next, let's calculate the factored tensile capacity, FTC, as the input tensile capacity of 180 kilonewtons divided by the tensile capacity reduction factor of 1.5, which is 120 kilonewtons. This is the value of pull-out load that cannot be exceeded. Otherwise, we're at the tensile capacity of the reinforcement. We are now ready to set up a basic analysis in slope W. The problem geometry consists of a 10-meter vertical excavation. The material within this region here, if I click on Draw Materials and Define, is labeled backfill with a unit weight of 20 kilonewtons per square cubic meter, a friction angle of 30 degrees, and a cohesion of 0. According to active earth pressure theory, this excavation would not stand. The factor of safety would be exactly 1.0, and the critical slip surface would be inclined at 45 degrees plus the friction angle divided by 2, which in this case is approximately 60 degrees. We're adding these 4 layers of geosynthetic to stabilize this slope and increase the factor of safety. Creating a geosynthetic or any reinforcement is similar to a material. I can click on Define, Reinforcements to bring up the dialog box. We can add one, clone one, and so forth, just like materials. In this case, we have our user-defined pull-out resistance already created. From the drop-down menu, we've selected geosynthetic. Alternatively, we have anchor, nail, pile, and then our manufacturing reinforcement that I'll get to shortly. For this problem, as noted in the PowerPoint, the pull-out resistance is 75 kPa, the reduction factor is 1.5, tensile capacity, and tensile capacity reduction factor. You'll notice that further down, we have our 75 kPa divided by 1.5, giving us our factored pull-out resistance that we calculated by hand of 50 kPa. And similarly, the factor tensile capacity is 120 kilonewtons per meter of fabric. Close this dialog box and simply note that there are 2 different ways to draw reinforcement. We can draw reinforcement sets or one reinforcement at a time, which we've done for this particular problem. Once we select this, we choose the reinforcement and then simply click and click to draw one. I'll hit Ctrl Z after closing the dialog box and we'll move on. Under Define Project, we see that we've added a single analysis and labeled it 1, base case, and then a second one, pull-out resistance calculated. We have a single default 2D geometry in here. With that done, we've selected the Morgenstern price analysis method using a half sine side function. On the slip surface tab, the direction of movement is left to right, and we're searching for the critical slip surface using entry exit. Close that dialog box, toggle off the second analysis. In results view, we see that the critical factor of safety is 1.45. On each reinforcement, we also notice a small box drawn from the edge of the critical slip surface towards the end of the reinforcement. I'm going to click on View Object Information and select the lowermost reinforcement. Focusing on this dialog box, we see the inputs near the top, the geometry of the reinforcement, and a little bit further down, here's the max pull-out force that we calculated in the PowerPoint. The length of reinforcement behind the critical slip surface is 1.66 meters. If we take 1.66 meters and we multiply by our factored pull-out capacity of 50 kilonewtons per meter, we arrive at the full pull-out force of 83.18 kilonewtons. Now, because the pull-out force that was calculated based on the length behind the slip surface is less than the factor tensile capacity of 180 kilonewtons, we see this flag stating that the pull-out resistance is the governing component for this particular reinforcement. I'm going to click on the fifth slip surface in the list. And now we'll look at the lowermost reinforcement. Now this was the one I was actually using in our hand calculations. The length behind the slip surface is 7 meters. 7 meters times 50 would far exceed the tensile capacity. And so in this case, you'll notice that the reinforcement is drawn with a dotted line. Because we have reached the tensile capacity, the pull-out force is 120 kilonewtons, and the governing component is set to tensile capacity. We also note that the red box now does not extend to the back of the reinforcement. That's because if we take this length right here, the length required to reach the maximum is 2.4, but we have 3.67 meters. That's from here to there is 3.67. We only need 2.4 meters to reach the maximum value. I'll go back to the critical and select the Draw Graph button and review the convergence plot. For convergence plot for a Morgenstern price or Spencer type of analysis is factor of safety versus lambda for both the moment and force factor of safety equations. So given the formulation, as we change lambda, it alters the shear that develops on the edge of each slice, and therefore changes the equilibrium of the system. For this slip surface right here, the crossover between the force and moment lines is unambiguous, and so this is a well-converged solution. If I select the next slip surface down, we see similarly that the convergence is quite well behaved. In fact, these top 5 are generally well behaved. You'll notice that this slip surface did have a little bit of oscillation right here. This one seems fine, along with this one. Now, once we get past these top 5, you'll notice that all other slip surfaces in this list did not converge. The E981 error message means that a factor of safety could not be calculated at a lambda value, certain lambda value of 0, or some other specified lambda value. So those ones are non-converged. And then these ones right here, we see that over the lambda range specified, once we got close to 0, it couldn't calculate a lambda, and so the solver could not find a converged solution. With that stated, I will return to the PowerPoint. Convergence problems can arise due to 3 main reasons. First, high strength contrast between adjacent materials. Second, sharp corners in the trial slip surface. And third, concentrated point loads. Ultimately, the last 2 issues are the same as the first issue because sharp corners and point loads often cause an increased effective base normal stress, resulting in increased strength on a particular slice. Recall in the limit equilibrium formulation that the factor of safety is defined as the factor by which the strength must be reduced to bring the slotting mass into a state of limiting equilibrium. 2 slices with vastly different shear strengths make it difficult for the solution to find a single factor of safety to satisfy equilibrium over the whole. We can solve this problem by reducing the strength contrast. In dealing with point loads, such as reinforcement, we need to distribute the load over many slices versus concentrating it on a single slice. I will return to slope W to demonstrate. Clicking back on Define View, first back to Results, I'll note that if I draw or view slip surface information and select on any slice that intersects the reinforcement, we see a concentrated point load on that slice. Similarly, if I click on Draw Graph, Add a Graph, and plot the base normal versus slice number, we see that point load reflected in the effective base normal on these slices. And in turn, if I clone this graph and plot the frictional strength, we once again see that the increased effective normal resulted in an increased frictional strength for those slices. I'll now click back on Define, Define Reinforcements, and note that in this dialog box, we have the option for the force distribution to be concentrated versus distributed. As the name implies, selecting this option distributes the reinforcement load on all slices from the intersection point down towards the toe of the slope. If I close this dialog box and resolve, we will note that the factor of safety for the critical slip surface is effectively unchanged at around 1.4 and a bit. Notice, however, that once we get beyond the top 5 slip surfaces, all of these slip surfaces below there now have a factor of safety up to around this one right there. If I click on Draw Graph and choose the factor of safety versus lambda convergence plot and begin to toggle my way through these slip surfaces, again we see that the convergence is a lot more acceptable for many slip surfaces. I'll now close this dialog box, go back to the definition view, define project, click on the Advanced tab, and I'll switch the search method for the solver from linear to root finder. As this name implies, the linear search increments lambda according to the input values in this table. This linear search technique is not nearly as efficient as the root finding method, and nor can it handle more difficult convergence problems. Closing this dialog box and resolving, going to the convergence plot, you will note now that, unlike before, even the trial slip surfaces further down the list exhibit very unambiguous convergence. Now, let's discuss the issue of internal versus external stability for mechanically stabilized earth walls. It's important to differentiate between internal and external stability. Most mechanically stabilized walls include wall facing, geogrids, backfill, and then the naturally retained material behind the wall. The MSE wall can effectively be thought of as a single block. In this case, the mode of failure under consideration in slope W is either circular or base sliding. We could therefore use the entry-exit search technique to explore a circular mode of failure, or the grid and block search to investigate basal sliding. In contrast, internal modes of failure give consideration to a bilinear failure that passes entirely through the MSE wall. The image shown here comes from a Federal Highway Administration publication in the United States. The breakpoint of the bilinear curve is at half of the wall height, unless the wall is battered or the ground behind the wall slopes. The load resistance at each of the reinforcement layers is compared using a semi-empirical analytical solution. The tensile load induced in each layer is calculated using a slightly modified version of the Rankine earth pressure theory. The pull-out shear resistance is determined essentially using an interface coefficient of friction and the vertical effective overburden stress. The point of this short description is to note that internal stability calculations are used directly to determine if the tensile capacity of the reinforcement will be exceeded under loading conditions. Slope W is ultimately used to check if circular or basal sliding could occur. Although slope W analysis could be used to check for a mode of failure that sits within the MSE wall, the analysis will often suffer from convergence problems due to the number of reinforcement point loads applied to the sliding mass. It is therefore recommended that caution be used when analyzing internal stability with slope W. Now let's review a case study. Today we're going to look at an MSE wall constructed to accommodate a roadway along the perimeter of a steep slope using a McAfee TerraMesh rock wall system. The TerraMesh system consists of pre-assembled wire mesh unit cells used to confine the stone. The cell is constructed using a continuous panel of mesh that comprises a base fascia, a lid, and a diaphragm or dividing wall. The length of the base behind the gabion is project specific. The stratigraphy for the problem comprises foundation soil, backfill, and structural soil, which is used as the backfill behind the gabions. The MSE wall was constructed in 4 benches, with battered walls having a face inclination of 5.7 degrees from vertical. Construction commences with the placement of the gabion system. Each gabion had a height and width of 1 meter and 2 meters respectively. The steel wire mesh base extended to a length of 10 meters behind the face of the wall. Structural soil was placed behind the wall up to grade with the top of the gabion. A McAfee Paralink 300 geogrid was then installed prior to the construction of the next lift. The length of each Paralink geogrid was governed by the distance from the wall to the face of the hill slope. Let's now turn to GeoStudio and review the setup of this analysis. The first thing I'm going to do is navigate to Define Project and add a 2D geometry to the file. With that done, I'll go to File and import a DWG file that contains the design geometry for the site. Using the options, I'll translate the geometry to the 0, axis and only bring in the material information from the CAD file. Okay, with that done, I'll hit apply and we see that the MSE wall, backfill, and all the materials have been brought in. So I'll close this dialog box and then go to Define Project again. And under our 2D geometry, I will add a slope stability limit equilibrium analysis. It's going to rename this Analysis 1, no reinforcement. I'll click on the Slip Surface tab. You see that it's set left to right, and we're using Entry-Exit. I can now go to the Draw Entry-Exit. I'll click and drag open an entry zone, and then click and drag an exit zone. You can see here just by the setting that I'm trying to check the global stability before reinforcement is installed. With that done, we'll go to the materials and simply note that each material is currently set to more Coulomb, and as noted, the material colors and everything came in with the import. I'll add a materials table just for our own reporting. So that's done. I'll click on the Styles tab and change the font. And then modify the contents by clicking on the Content tab and turning off the material model and the phi b input, which of course is 0 for all the materials. Okay, we're now ready to solve. You notice in the Solve Manager that the toggle is on, and I'll hit the Start button. Okay, in Results View, notice over on the left, in the tab there, in the docking window, we note that the factor of safety is very low. It's 0.3 and a bit. So clearly the system is in disequilibrium, and hence we need to install some reinforcement in this problem. Also note that the convergence shown by the factor of safety versus lambda plot looks unambiguous and is therefore very reasonable for these slip surfaces. One thing I don't particularly like is the steepness of the slip surface. It far exceeds the active earth pressure coefficient, so I'm going to make an adjustment for that in a second, right after I adjust the color map so that it spans the same amount of color range as the slip surface color map. So I'll just do that, and then I'll hit the close button. Okay, like I said, that's quite steep, so I'm just going to go back to the define view and then adjust the entry-exit zone. I'm just going to back the entry up a little bit, and while I'm here, I'm also going to refine the number of increments on both the entry exit side and the radius increments, just so that we have a higher resolution in our search. Okay, just double checking that everything looks good before progressing. I'll hit the Start button again. And we see that if I go back to auto select the critical, the factor of safety remains very low. Notice now that the critical is very linear, so it's more in keeping with an active earth pressure wedge behind a retaining wall. Okay, I'm now going to go back to Define Project and click on the Add button, clone the analysis, and now rename this to analysis number 2. This one is going to include reinforcement. So just name it reinforcement. And you'll see here later on, I'm going to explore the effect of a seismic coefficient and other changes. So this one is without seismic. I'll zoom in to our area of interest. And now we'll explore adding the reinforcement. The first step is to click on Define Reinforcements. Notice that the list has not been populated, and so I'll click on the Add button, and then in the reinforcement here, I'll just rename this Paralink 300. Okay, and then from the Type dropdown, I will select from our list Macafar. You'll notice that we have Husker, Tenkate, and Tensar as our manufacturer libraries. From the model list, we want the Paralink GeoGrid. And down at the bottom here, you'll notice that the dialog box is split into calculated parameters and input parameters. So starting at the top, we need to adjust the product line from Paralink 100 to Paralink 300. And the next in the list is the D50 particle size or backfill. So I'm going to change that from silty sand to coarse gravel, 13 millimeter coarse gravel. And the fill material needs to change. It is not a clay, it is a sand, gravel. So choose gravel. Internal friction angle. Oh, sorry, notice as I scroll down here that the overall reduction factor pullout coefficient gets set as I make my selections. So I'll go and enter in an internal friction angle of 30 degrees. The pullout resistance reduction factor we leave set to 1 because all of the different settings that control the factor are automatically set for. So just going down the list here, we have temperature, we'll change the design life to 60 years, and then pH just fine. Face anchorage is yes, because the geogrid is attached to the outside of the Gabion blocks. Factor of safety dependency is left a no, and we are going to distribute the load always for these manufacturer ones because it helps with convergence. Now with these set, we see the pullout coefficient is 0.9 and the interface shear angle is 27.5. I'm just going to switch to this document here and just remind us that the interface shear angle, according to equation 3, is the inverse tan of our pullout coefficient, which is 0.9, multiplied by the tan of our input interface friction angle, which in this case was 30 degrees. So it's that pullout coefficient that helps us arrive at the actual interface shear angle of 27.46. Okay, next, the tensile capacity of this product, according to the specs, is 301 kilonewtons. Our selection has given us an over-design factor of 1.09, and I'll just note again back in the document that the factor tensile capacity is calculated by dividing the TC by a number of factors that include installation damage, weathering, chemical environmental effects, creep, and even reduction due to extrapolation of the data. So that's where the 1.09 comes from and the 275 kPa. Okay, the surface area factor by default is set to 2, and you cannot change that for the manufacturing reinforcement because it is assumed that shear mobilized is on both sides of the reinforcement. Okay, now we need to create some reinforcement on the domain. So I'm going to click on Draw Reinforcement Sets. In this dialog box, the first thing I'll do is select our reinforcement and then rename it to Paralink 300. Okay, these reinforcements are all horizontal, so select that option. We'll set the length while we draw them, although you can go back and refine that afterwards. Clicking once on the face and then again on the face, we end up currently with 4 reinforcement. So coming over to the spacing, I'm going to change that to 8, and then I'll close this dialog box. So there's our first set of reinforcement in the lower block of the MSE wall. Okay, so if I go to define reinforcement sets, you'll see that there's only one in the list. And again, we have our one reinforcement here. I need to quickly change this. I realize I chose evenly, but I want a spacing of 1 meter. Okay, clicking on draw again, reinforcement sets, and once again selecting the same options as before. This one though is for group 2, so that next level up. Choose horizontal, and then switch this from evenly to vertically, and enter in a spacing, vertical spacing of 1 meter. With that done, I'm going to click not at the bottom of this course, but on the top, and you'll see why in a second. So the length goes to the back of the backfill, and then when I click and bring out to the face, because I've set the spacing to 1 meter, I don't accidentally get a reinforcement at that lower level on top of the other layer. So that's why I started from the top down. Then I'll just select the reinforcement type. Okay, in the interest of time, I'm just going to switch over to a fully built system, just because it takes a little while to draw the reinforcement. So we have a number of analyses in here, including reinforcement without seismic. Then in this analysis, we introduce a seismic coefficient by going to define seismic coefficient and entering the following. In the analysis number 4, we check global stability by changing the location of the entry and exit zones to make it a more global check. And then in the last 2 analyses, we adjust the exit zone so that we have a slip surface passing through that second lowermost portion of the MSE wall and then the lowermost. So those are our checks on, we say internal stability, but ultimately it's a different mode of failure that has a shallower slip surface. Okay, zooming into our base case without seismic, we see that the factor of safety is 1.523. And notice that the critical slip surface is located predominantly behind the geogrid. Now, naturally, that's what we expect to happen because the geogrid forces the slip surface deeper into the profile. Also, the convergence looks really good for all the slip surfaces. It's unambiguous, nice clean crossover between factor of safety, force, and moment. Okay, I'm going to close this dialog box and then zoom in and click on the View Object Information just to review some of these reinforcement. So this lowermost one, notice the dotted line is showing. That's because the tensile capacity is the governing component. Given the depth of the reinforcement, which is calculated from the intersection of the reinforcement with the slip surface up to the ground surface, the pullout force is around 98 kilonewtons per meter. So given the length available behind the slip surface, this one reaches capacity. Notice the second one up, the box is much smaller, and that's of course because the overburden stress is higher. It's mobilizing increased level of pullout force and therefore reaches tensile capacity with even less distance behind the slip surface, and that's true of all the reinforcement above there. Now, if I click on a different slip surface, once again, you can see that the tensile capacity of the reinforcement governs for most of those layers of reinforcement. Okay, just clicking on some of the slices, we see that the point load from the reinforcement is indeed included. We've distributed the load, so despite the high density of reinforcement, we see point loads on every slice, because of that setting. Okay, when we increase the seismic coefficient or include a seismic coefficient, the factor of safety goes down a bit. The global stability check, we see that the factor of safety is around 1.53 with the exit way down at the toe. And then if we check any slip surface that captures more of the MSE wall and the reinforcement, once again, the slip surface is pushed towards the back of the reinforcement and the factor of safety is well above 1.5. And in this case, it's 2.6. Okay, I'll just return back to the PowerPoint for some concluding statements. Conducting a stability analysis of mechanically stabilized earth walls in GeoStudio requires consideration to soil structure interaction, convergence, the issue of internal versus external stability, and the workflow required to set up an analysis. This webinar highlighted the assumptions implicit in a limit equilibrium analysis, namely that MSE walls involve complex soil structure interaction in which pretensioning and/or deformation causes load to be transferred into the reinforcement via the connection at the facing. The shear mobilized at the interface between the reinforcement and the soil or rock is either entered as a pullout resistance or it is calculated as a function of effective overburden stress. This pullout resistance is factored to account for installation damage, temperature, and more, then converted into a reinforcement load based on the length of reinforcement behind the slip surface. It is critical in an all slope stability analysis, and especially when reinforcements are involved, to review the factor of safety versus lambda convergence plot because point loads lead to high base normal stresses which manifest in high strength contrasts between adjacent slices. This is the fundamental cause of convergence problems in a limit equilibrium analysis. Keep in mind that slope W should ultimately be used to address the overall stability of the retained system and not to analyze internal stability, which approximates the load in each individual layer of geosynthetic and compares this value to the tensile capacity. Finally, slope W provides a number of features to support the workflow for analyzing MSE walls, including manufacturer libraries for geosynthetics, and a number of user interface tools to create multiple reinforcement, and the ability to explore different modes of failure using the cloning feature within the analysis tree. A short survey will be available after the webinar. Please take a couple of minutes to complete. Thank you very much for taking the time to watch this webinar, and we hope to hear from you.